Okay, so in this last talk we will see applications of methods of index theory to the Selberg's trace formula. But before, I would like to give us just a final compliment to the last lecture. So I will explain in more detail, a little bit more detail, what is equivalent metric. So let X be a compact complex manifold. Let GTX be a Hermitian metric on the holomorphic tangent bundle Tx, and let EGE be a holomorphic Hermitian vector bundle. Okay, so I will consider the Dolbeault complex of anti-holomorphic forms with coefficients in E equipped with the Dolbeault operator. I also define the natural L2 Hermitian product on this space with a proper normalization. I mean, there is some normalization here to introduce. The normalization actually will not appear in what I will say, but anyway. So 1 over 2 pi to the n, where n is a dimension over C of x, integral over x of S prime dx. So then I introduce the adjoint d bar x star, the L2 adjoint, with respect to the L2 Hermitian product. Then an analog of the Dirac operator, which is d bar x plus d bar x star, and the corresponding Hodge Laplacian, which is the anti-commutator or the supercommutator of d bar x and d bar x star. So by Hodge theory, we know that the kernel of dx star of dx squared can be identified canonically with the cohomology, holomorphic cohomology of x with coefficients in E. So because the kernel of dx squared is embedded into the Dolbeault complex, so they are made of smooth forms, it inherits a certain Hermitian metric, which I call G kernel of D squared. So this is a finite dimensional Hermitian vector space. So definition, I define lambda to be the following complex line. It's an alternate product that's the determinant line of x0 with coefficient in E, so h0, 0, 10-third determinant of h0, 1 of x and E minus 1. So minus 1, I remind you that's a dual, 10-third, etc. So that's an alternate product of complex lines. So lambda is indeed a complex line, and lambda is a complex line. That's a so-called determinant line of the cohomology, and I define lambda to be the metric which comes from this harmonic forms. That is, I just identify the cohomology with the harmonic forms. Identify the cohomology with the harmonic forms, and then this is a metric induced by the metric G kernel of D squared. So this metric is not a good metric from the point of view of direct images, because it tends not to be smooth when you consider families of complex vector bundles, complex manifolds. So we are going to define the holomorphic torsion. So for real part, yes?
What is the determinant of
So this is, I defined it last time, it's lambda max. Okay, determinant of vector space, it's a lambda max. Okay, that's a lambda max, so it's a line, a complex line. So for real part of S bigger enough, in this case bigger than the complex dimension, I define theta of S. So theta of S will be typically a sum of zeta functions associated with S. So let me just say this. I define it as the sum of -1 to the p plus 1 times p times zeta p of S, where zeta p of S is just the sum of lambda to the minus S with lambda in the spectrum of dx squared restricted to the p forms, to the 0p forms. And of course here I take lambda positive. So in other words, I exclude the zero eigenvalue and I just take all the collection of eigenvalues of the Laplacian and I form this, lambda to the minus S. So this is so-called zeta function, and it's well known that zeta p of S extends to a meromorphic function which is holomorphic at S equals 0. Which is holomorphic at S equals 0. So in particular, theta of S is holomorphic at S equals 0, and by definition we define analytic torsion Tn to be equal to the exponential of theta prime of 0. So this is a spectral invariant. In other words, this is a spectral invariant of the Laplacian. Of the Laplacian dx squared. So by definition, the Quillen metric lambda is equal to exponential, or maybe I just put an over 2 here, okay. So it's given by the L2, the metric I defined before, coming from the harmonic forms, multiplied by T, by Tn. Okay, so let me insist on the fact that traditionally Hodge theory was just used, in other words, to consider the harmonic objects. And basically, the whole rest of the spectrum was essentially ignored. Now, in this context, the definition of the Quillen metric, to the contrary, considers that, in some sense, all the eigenvalues are as important in this context. So you need whole spectral theory. And so let me quote theorem. So I now consider again this projection, holomorphic projection, proper holomorphic projection, holomorphic projection, submersion, and I assume that again I give myself GTX, GE, and so on. So I have actually, for instance, in this case, EGE is a holomorphic vector bundle on M. So maybe before stating a theorem, let me define lambda to be the determinant of the direct image of E. So this is actually a holomorphic line bundle whose fibers are canonically identified to the determinant of the cohomology of XS with coefficients in the restriction of the vector bundle e to the fiber XS. Okay, so the existence of such a line bundle is non-trivial. The only case where you can see immediately is through where the cohomology has locally constant dimension, but in general it is true. Okay, so then you can then define for every fiber you define the Quillen metric, the way I said. That is, you use the Hodge theory of the fiber, introduce the corresponding zeta function, and so on. So all these fibers are now equipped with a Coulomb metric. So let me state the theorem, which I proved with Gillet and Soulet. So the first thing is that the Coulomb metric is smooth. Okay, so the Coulomb metric is smooth on lambda. Okay, so this would not be the case. This would not be the case for the L2 metric. Okay, this metric in general is not smooth because of the jumps in cohomology, but if you multiply this by these two things, their discontinuities compensate each other, and it is smooth. And the second thing is, if M is scalar and GTX is fiber-wise scalar, then the C1 form, now we do have a line bundle equipped with a smooth metric. So then this, as I explained last time, this metric determines the connection, which is the so-called Chern connection, and you can calculate its C1 from the curvature. And the C1 is given by the integral along the fiber of Todd of Tx, GTx, Ch of EGE, and the piece of degree 2 here. Okay, so these characteristic classes are computed using the corresponding Chern connection. The metric determines the connection, which in turn determines the Chern-Weil forms. Okay, so this result, I mean, is remarkable because it says that in some sense the natural object, which is just sort of the right-hand side of Riemann-Roch-Grothendieck formula, now acquires another dignity because it's just the C1 for a certain canonical metric, which is a Coulomb metric. And essentially, the proof of this, okay, one key step is to use what I did in my previous talks. Okay, so is use transgression formulas from the family's index theorem. So I explained just one of them. It's more complicated than that, but essentially from what I did, you can get at least part. You can get at least part of the theorem. And so in effect, it is just the starting point of a whole theory of Coulomb metrics. The general problem will be, yes.
Where's the lambda?
Excuse me.
What is the lambda in the metric? I mean, metric is dependent from lambda. Yes?
No. Lambda is a line bundle. Okay, it's defined algebraically, if you like. Okay, and given the metrics, you put a metric on lambda. Okay, from the metrics down over here, you get a metric on lambda down here. Okay.
And what does it mean that it is lambda?
Okay, so I said that you do have this canonical line bundle, which is a holomorphic line bundle on the base S now. Okay, this is a line bundle, holomorphic line bundle on S. Okay, now fiber by fiber, you can construct the Coulomb metric because fiber by fiber, the fibers of this lambda S are canonically identified with the determinant of the cohomology. So you can construct using Hodge theory of the fiber the corresponding Coulomb metric. Okay, so what I'm saying now is that actually this metric is smooth on lambda as a line bundle. And this is, of course, not obvious because that means that the metric can, in some sense, understand the algebraic geometric construction of lambda. Okay, so there is an obvious case where it would be true in the case where the cohomology doesn't jump. So in this case, this is not too hard. But in the general case, it's a remarkable result that it is smooth. And besides, the curvature, essentially the curvature up to 2i pi, or minus the curvature of 2i pi, is given by local expression. Okay, so this connects, in some sense, the metric connection of the determinant bundle with local differential forms of the manifold M. Okay, so So basically, this is a starting point of a whole class of results, which I would explain in the following way. So from the algebraic theory of determinant bundles, you have certain canonical algebraic isomorphisms. Okay, so you can have, I will not explain in detail because I don't have time, you have certain canonical algebraic isomorphisms, or canonical, let's say, isomorphisms of lines, of determinant lines. Now, on the other hand, now our determinant lines become equipped with metrics. And the question is to know to what extent the canonical isomorphism of determinant lines transfers to an isometry or not. And so generally, certainly you do not expect this. So for instance, you can have determinant of cohomology of a small manifold, which is canonically isomorphic to determinant of cohomology of a big one. So these are algebraically isomorphic, but you certainly do not expect that the metric coming from the Hodge theory of the big manifold corresponds to the metric coming from the Hodge theory of a small manifold. And so that means that every time there is a canonical sort of algebraic isomorphism, there is a certain constant now which will measure to what extent the metrics differ. Okay, so in the end, yes?
What are determinant lines?
Determinant lines, they are sort of objects that I constructed here. Of the kind lambda, yes. Okay.
You said that there is a canonical isomorphism.
They are. Okay, so typically, let's just give an example. You take an embedding of projective manifolds. You take a vector bundle F on Y. Then you can, because of projective, you can resolve the vector bundle on Y by a complex of vector bundles on X. Okay, this is K theory now. We can resolve, we can find a sheaf, complex of sheaves of vector bundles on X, whose hypercohomology is the same as the cohomology of F on Y. And so then you can build a determinant of the cohomology on Y and on X. These two things are the same algebraically, and then you ask to what extent the metric differs on these two, the equivalent metrics. You have the equivalent metric coming from the small manifold, the equivalent metric coming from the big, and then you ask to what extent they are compatible or not. And so there is an answer to this question. Okay, so the answer is always that this canonical isomorphism can be measured by a local formula. Okay, this can be measured. The difference of metrics can be measured by a local formula, which means that in the end, up to local terms, you can expect to be able to completely calculate the equivalent metric just out of arithmetic data. Okay, so I will not go into this, but ultimately there is a theorem which gives you a formula for the metric in terms of arithmetic data of the corresponding scheme which is underlying the construction. Okay, so I'm not going into this. This is Riemann-Roch theory of Arakelov, Riemann-Roch theorem. I'm not going into this, but these properties of the equivalent metrics play, of course, a fundamental role. So let me insist again that the key point now is actually the real hero is this one, because where actually the non-zero spectrum of the Laplacian comes in, and in some sense, its role is exactly to permit to have a theorem like that, where the curvature would become local. Okay, so I'm now moving to something else, but again, before saying what I will do, let me just an observation. If we look at the index formula, or let's say the Riemann-Roch-Hirzebruch formula, let me just write it this way again, CH of E. We have here something which is global, that's the Euler characteristic, or the index, let's say, in general, which is expressed locally. So you express a local quantity in local terms. Now, there is another theory in which you have this exchange of local and global, which is Fourier transform. When you have a Fourier transform, when you have Fourier transform, we know well that if you have a function which is very delocalized, its Fourier transform tends to be very localized. And conversely, if you have a distribution which is very localized, its Fourier transform is very delocalized. So we're going to ask, in some sense, is there a sort of Fourier factor which allows you to pass from this side to this side? Is this, in some sense, an aspect of Fourier transform? Okay, so I will not develop a complete theory of this. I will just explain a special case which is the question of the trace formula. So let me just now take the case of X to be a compact real manifold equipped with a Riemannian metric GTX, and I just take T positive, and I take the heat kernel, exponential of T delta X over 2. And then I'm going to look at the trace of the heat kernel. So observe that I don't have now a super trace, so these traces do not have anymore a sort of topological flavor. They are no longer homotopy invariant. This trace in particular depends on the parameter T. So let me just change names. I just define G to be exponential T delta X over 2. Okay, so I drop the dependence on T, and so my question is that we want to evaluate the trace of G. And this will be on the space of smooth functions. So I want to evaluate the trace of the heat operator on smooth functions. Okay, so the question I'm going to ask is the following thing. Is this trace an Euler characteristic? Is this trace, question, is trace of G an Euler characteristic? Okay, so let me try to explain what I mean by this. So in the case, let me go back to the case where X was complex. And so what we had actually from the Dolbeault complex provides you with a resolution in the sense of homological algebra of the sheaf OX of E when I have a holomorphic vector bundle E. Okay, so I'm not going to repeat the assumptions. And so we do have the fact that the Euler characteristic of this vector bundle, which I will write as a supertrace on the cohomology of the identity, right? So chi of E is an alternate sum of dimensions, so it's the supertrace of the identity. I can write it ultimately as a supertrace of exponential from the index theoretic arguments that I gave. I can write it as a supertrace, let's say, divided by b squared. And I introduce a different parameter b to distinguish from the t before. Okay, so what we did in the context of index theory was to say we have the Euler characteristic, which is a supertrace of 1, and we write it as a supertrace of the exponential minus dx squared divided by b squared for any b. Well, more generally, okay, so maybe to simplify things, I will assume that there is a vanishing of higher cohomology in this model. In the model I take, I assume that there is a vanishing of higher cohomology. So in this case, basically you have the exact sequence, H00 of XE, which maps into omega 00 of XE, which goes through d bar of X to omega 01 of XE. And so this sequence is exact. It's an exact sequence. So saying that there is no higher, so here you have the embedding, here you have the Dolbeault map, Dolbeault map, Dolbeault map, and so this is an exact sequence, and so this is just saying, in other words, that the Dolbeault complex is a resolution of H00, resolves H00 of X and E. So basically then I will just cancel the supertrace and just write the trace of H0 of X and E is equal to the supertrace on the resolution. Well, more generally, in the same context, if G is a holomorphic diffeomorphism of the manifold X which acts on E, you can define the corresponding trace of G acting on the cohomology on the H0. In other words, a holomorphic diffeomorphism acts on holomorphic sections of E, and so you can define its trace. And basically, for the same reasons as before, you can replace the trace by the supertrace of exponential minus dx squared divided by b squared. So this I did not prove, but essentially the method of proof is the same, which is to say you can replace the computation of the trace on the cohomology by the computation on a bigger thing, which is a Dolbeault resolution. You replace the trace on the cohomology by an alternate sums of traces on the Dolbeault resolution, and by making B tend to 0, making B here tend to infinity, what you get is a Lefschetz formula. Which is to say an integral on the fixed point set of G. So basically, having this example in mind, what we're going to ask is the following thing. Now, can we think of the space of smooth functions on the manifold X? Can we think of this as the cohomology of some complex?
How did you get this formula? We didn't have a with X on our
Sorry? So you get the Lefschetz formulas exactly by the same method as I gave in my course, by making t tend to 0, in this case by making b tend to infinity, and the supertrace localizes on the fixed point set.
But Lefschetz formula is for the case where a group X.
Yes.
Do we have a group?
Yeah, okay, I gave myself a G, right? I gave myself a G. It's enough to give yourself an element of a group. You don't need to have a full group, right? You take a specific element, a G acting, and generates a group, if you like.
But G is exponential of Laplacian.
You're right. You're right. So it's not the same situation. It's not the same situation now. Okay, that's just an analogy. I'm making an analogy. I gave you the analogy of a diffeomorphism acting on a complex manifold, and then I get the trace of its action on the cohomology as a supertrace on the Dolbeault resolution. Now I'm saying I give myself the smooth functions on the manifold that has nothing to do, equipped with a G action of G, which is now the heat kernel. And I want to think of the smooth functions on the manifold as the cohomology of something. Okay? So in other words, we deal with an object which is not naturally a cohomology group, and we want to think of it as a cohomology of something. Okay? And so basically, if we could do this, so it would be the cohomology of some complex RD. Okay? And we would hope that the action of G lifts to the complex as a morphism of a complex, exactly like in the holomorphic case, when you have a holomorphic diffeomorphism, the action lifts to the Dolbeault complex, and it defines a morphism of the complex. So we would hope that G lifts to a morphism of the complex, so that we would re-express G, the trace of G, the trace of our original heat kernel, as being the supertrace of G exponential minus D square over B square. We would have something like this. So that's a question, in other words. Okay? That's passing from the cohomology as being given naturally, as saying, is the object which is a smooth function of the manifold, is it the cohomology of something? And can I hope, in other words, to exploit this resolution to get something which eventually will be the trace, Zelberg's trace formula? So that's a question. By making B, if we have this, by making B here tending to plus infinity, which corresponds to make in the previous course t tending to 0, we would get a formula which will be Zelberg's trace formula. Okay, so the basic difference with what I'm saying now is that, of course, the cohomology that we have here is infinite dimensional. Okay? The cohomology we have here is infinite dimensional, first, and the second thing is that it's not naturally given as a cohomology. Okay? So we have to invent a cohomological theory such that the space of smooth functions is its cohomology, and then use it as a tool to prove something like the trace formula. So first of all, let me observe that any vector space is the cohomology of itself. Okay, so saying, is it the cohomology of something? This is fairly obvious. Okay, so it can be the cohomology of itself. But now, let me give a more precise thing. So let E be a real vector bundle. Let me put this in a more general framework. Let E be a real vector bundle on X. And I'm going to consider actually, this will be the RAM. Now there is no longer holomorphic thing, so this will be the RAM just of the fibers equipped with the de Rham operator along the fiber. Okay, so what this means, I just look at the collection of the fibers and I take the relative de Rham complex, the de Rham complex along the fiber. Okay, so in other words, I take smooth sections of the exterior algebra of the fiber equipped to the fiber-wise de Rham complex. So using the Poincaré lemma, which says that the cohomology of a vector space is concentrated in degree 0, what we know is that the cohomology of this object here are just the forms which are constant. They are just of degree 0, and they are constant along the fiber. But a function on the total space of E, which is constant along the fiber, it is a function on the base. So that indeed, this is a resolution of the space of smooth function on X with values in R. Okay, so we can write in effect, we have the exact sequence, infinity of X and R, 0 embeds into omega 0 of E, to omega 1 of E, and so on, and this is exact. So we do have this. Okay, so however, in general, it's very difficult to lift the action of a heat kernel to the resolution. So before proceeding, I will also say that if we want to apply this mechanism, we need to devise the proper Hodge theory. In other words, when we have this resolution, we need to understand what is the Hodge theory of the resolution. So in other words, we need to understand what is the Hodge theory of the relative de Rham complex. Okay, because the relative de Rham complex is precisely one of these resolutions. So I'm just going to say something now which is very easy in some sense. I will just make a few purely algebraic considerations, So let's forget about the situation here and some algebraic considerations. So let E be a finite dimensional real vector space. So I introduce these algebras, the exterior algebra, the symmetric algebra, so this provides you with multiplicative functors in the proper category, and also I introduce the algebra A of E star, which is the tensor product of A of E star times lambda of E star. I just take the tensor product of the exterior algebra times the symmetric algebra. Okay, so the symmetric algebra actually is the same thing as the polynomial algebra of E. Is canonically the same thing as the polynomial algebra of E. So these two algebras are canonically Z-graded. The grading here corresponds to the grading of the polynomials. And so this space here is just a space of polynomial forms. On E. So I introduce the theorem operator. Let me introduce the theorem operator. The theorem operator theorem, and so it acts on this A of E star. Okay, theorem operator acts on the polynomial algebra, and it's a basic thing that the cohomology of this complex, A E star D, its cohomology is concentrated in degree 0 and is just canonically R. Is just R. So A of E star gives you resolution of the one-dimensional line. So let me now introduce a metric GE, a scalar product, say. So in this case, lambda of E star and S of E star become themselves Euclidean vector spaces. They acquire a scalar product. They get the scalar product. Okay, and then what you can, okay, symmetric algebra gets obviously a scalar product. The symmetric algebra, you have to do some explicit normalizations. It's very easy to do. So A of E star becomes an Euclidean, infinite dimensional Euclidean algebra. And you can try to find what is the adjoint of the operator D with respect to this Euclidean structure. And so what you find is that the adjoint of D is just actually the contraction, by the canonical vector field Y. Okay, so maybe I should say that when I identify S of E star with the polynomials on E, there is then this canonical variable, which is Y in E. And so, actually, this is just a contraction by the vector field Y. Okay, actually, the operator D increases the degree in the exterior algebra by 1 and decreases the degree in the polynomial algebra by 1. And to the contrary, this contraction decreases the degree in the exterior algebra by 1, but increases the degree in the polynomial algebra by 1. So this is the adjoint of D. That's a very simple computation, and you find that this adjoint actually does not depend on the metric. So the corresponding Hodge Laplacian, the Iy, the anticommutator of D and its adjoint, D star, this is just by Cartan formula, that's a Lie derivative operator associated to the vector field Y, and this actually, it's simply the number operator of lambda of E star, or if you like, it's of lambda of E star plus the number operator on S of E star. So these number operator count respectively the degree in the exterior algebra and in the symmetric algebra. Okay, so, okay, in other words, the number operator of symmetric algebra acting on a polynomial of degree p acts by multiplication by p, and similarly on forms of degree q, this other one acts by multiplication by q. So this is Hodge Laplacian, and of course it shows immediately, I mean, that this is, actually, this operator is self-adjoint, is positive, and of course, I mean, by Hodge theory in some sense, you get the proof that the complex is exact and gives you a resolution of the real line, because this operator, of course, is strictly positive, and its kernel corresponds just to the polynomials of degree 0 and forms of degree 0, which are the constant. So this gives you a Hodge theoretic proof of the fact that the Durham complex, polynomial Durham complex, resolves the constant. And actually, this proof is exactly the one that you use. That's a classical proof of proving that the complex is exact and resolves the real line. Okay, so let me now explain what is the Bargmann isomorphism. Okay, so the Bargmann isomorphism will allow to pass from this, in some sense, from the algebraic Durham complex to the smooth Durham complex. So Bargmann was a physicist, so I introduce the following map definition. So I write it this way: it's a heat kernel with a round sign, exponential minus half of delta E. This is going to map S of E star into S of E star. Okay, so what do I mean by this? So I'm saying, first of all, that the Laplacian acts on polynomials, and it decreases the degree by 2. So we have here a heat kernel with a wrong sign. So we should not take this exponential in the classical sense. We should simply expand the exponential into powers by usual power series. So this is 1 minus 1/2 of delta E plus square and so on. And so you see that when acting on polynomials, expansion just stops. So there is indeed a map from f of E star to S of E star, and this is a filtered map. That is, it maps polynomial of degree smaller than p into polynomials of degree smaller than p. So this map is well defined. So there is a basic result that I remember fact or theorem. That's not a complicated thing, that this map extends to an isometry of the Hilbert completion of S of E star. This is a Hilbert completion with the L2 space of E with respect to the Gaussian measure. With respect to the Gaussian measure. So dME is just a Gaussian measure on E, the canonical Gaussian measure. Okay, so let's try to understand this. So first of all, polynomials are obviously embedded into L2 of the Gaussians for the Gaussian measure. So this map here can be viewed as a map from S of E star into L2 of E for this Gaussian measure. So the Bargmann isomorphism says that actually it extends to an isometry. The completion of the image is just equal to the L2 of E star. Okay, so in other words, if you like, you could view this as saying that you get from this isomorphism a canonical orthogonal basis of the L2 space from the image of the polynomials. So let me now explain what the Bergman isomorphism is. There is, again, this is very easy to find, a canonical isomorphism from the Gaussian L2 space to the classical L2 space of E with respect to the classical Lebesgue measure, to respect to the Lebesgue measure. In other words, I mean, maybe I could describe it directly here as being exponential minus a squared over 2. You have to work this out, divide by 2p to the n, and f of square root of 2y. So you just find that this map, this is a triviality, which maps the L2 space for the Gaussian to the classical L2 space. And so by composing the two isomorphisms, you get the Bergman isometry, which goes from the completion of E star to the L2 space of E, to the classical L2 space of E. Now, one can ask what happens to the operator, to the number operator, which counts the degree on E star. We have this operator which counts the degree on E star, on S of E star, and we can just try to find what happens to it when you identify S of E star with the L2 space of E. Right? So the operator which corresponds here is the so-called harmonic oscillator of the vector space E. It's an explicit operator, which I write this way, minus n. This is a so-called harmonic oscillator of E. That's a partial differential, elliptic differential operator. And so because of this in particular, because these two spaces are isomorphic, you discover also that the spectrum of HE is equal to the integers, because the spectrum of this one was given to the integer given by the integers. And besides, you even find what are the canonical sort of diagonalization. You even find the eigenvectors, because this operator is obviously diagonalized, and so you get the eigenvectors of this one by applying the Bergman map. Okay, so let's try to see now, when we identify S of E star tensor lambda of E star, we are going to identify it, let's say, with L2 of E tensored with lambda of E star. And we complete here. Okay, so I'm just taking the L2 space for convenience, because I don't have time to say more, but we're passing to the view where we have the sort of algebraic theorem complex. We apply the Bergman isomorphism, and we try to see what happens on the other side. So if we do this, we have the theorem operator here. This one becomes the so-called Witten twist. So this is just a conjugation of the operator dE by the Gaussian function. It's adjoint dE star, which is just a contraction by y. This becomes 1 over square root of 2 dE star, so dE star, sorry, the classical adjoint, plus the contraction by y. And so finally, the Hodge Laplacian on the algebraic side d star on the algebraic side corresponds to the Witten Laplacian, so-called Witten Laplacian, which is the sum of the harmonic oscillator plus the number operator acting on lambda of E star. Okay, so this means that now, in effect, the point of this is that because the cohomology of this complex, we know what it is a resolution of the constants, we also know what is the cohomology of this complex on this side here. So in particular, what we find is that the kernel of this HE plus n of lambda of E star, this will be generated, it's one-dimensional and generated by the Gaussian function. So in other words, via the Bargmann isomorphism, we have a cohomological theory which is very elementary, which is the one, that's just a causal complex, if you like, or the algebraic de Rham complex, and it maps to something which is not entirely analytically trivial, in which the cohomology now is represented by the Gaussian function. Okay, so let me try to explain now how to set up the proper language in which the computation of the Bargmann of the trace of a Hit kernel will become the computation of the computation of Lefschetz trace. So let G be a reductive group, a reductive Lie group with Lie algebra G and Cartan involution theta. So then G, the Lie algebra, splits as P plus K. I'm sorry, I'm not going to write this in Fraktur. In German things, not so good, so I just use Latin letters. So definition. I'm going to introduce the Casimir. Okay, the Casimir. CG is the Casimir of G, and this CG is an element of the enveloping algebra of the Lie algebra. So the enveloping algebra is just the set of invariant differential operators on the group G. Okay, so to define it, I should say that I did not explain this, B to be a symmetric bilinear form on the Lie algebra, which is such that this splitting is orthogonal, and B is positive on P and negative on K. So basically, generally, a reductive group comes naturally equipped with such a bilinear form. It can be typically, but not always, the killing form. Okay, so the killing form, the classical case, groups like SLNR and so on, there is this B. So what is the Casimir? So the Casimir is given by the following formula, is given by the sum of EI star EI, where EI is a basis of the linear algebra G, and EI star is the basis of G dual to the basis EI with respect to the bilinear form B. So if you have a non-degenerate bilinear form, if you have a basis, you can define the dual basis with respect to the form B. So this is a definition of the Casimir. Okay, so this should be viewed as invariant vector fields on the Lie group G. That's a Casimir.
Sorry, what's P and K?
Okay, so P and K, this, you have the Cartan involution. These Cartan involutions actually acts, these are the eigenspaces of the Cartan involution acting on the Lie algebra. Okay, so you have the Cartan, the involution of the Lie group, theta square is equal to 1, that's an involution, and then it's a group homomorphism, it acts on the Lie algebra, and so the Lie algebra splits naturally as P part and K part. Okay, so in the case of SL2R, say, P is just the self-adjoint matrices of trace 0, and K is the antisymmetric matrices. Okay, that is just a obvious splitting. You take trace-free matrices, 2 by 2 trace-free matrices, it's split as the self-adjoint ones and the skew-adjoint ones.
They do not have to be really subalgebras.
Sorry?
They're not subalgebras necessarily.
No, P and K are not subalgebras. K is, but not P. Okay, K is, but not P. Of course, the Lie bracket of 2P lies in K, so it's not. Okay, so this is the Casimir operator. Okay, so the point about the Casimir operator is this one. Okay, so let K be a maximal compact subgroup. The maximal compact subgroup which is fixed by theta. Okay, so maybe to fix IDs, if G is LCL2R, theta is just G transpose minus 1, okay, and K is just the group, is just the isometry, so K is just S1 embedded in SL2R. These are the isometries of the vector space. So essentially the rotation group. The rotation group of R2 embeds into SL2R. So in general, K is a maximal compact subgroup. And I define the symmetric space X to be G over K. Okay, so this inherits a Riemannian metric. Well, I should say this is because it's very easy to see that Tx is just, I write it as a quotient bundle G quotient P. Okay, it's the group K acts on P. This is very easy to find. It preserves the splitting actually, and Tx is just G times Kp. And this action being isometric, then there is a canonical Riemannian metric, GTX on X. So X is a Riemannian manifold. Now, the Casimir operator, as I said, acts on C infinity of G and R, and by pullback, it induces an action on C infinity of X and R. Okay, if you have a smooth function on X, it lifts to a smooth function on X, on G, and so you can have the Casimir acting. And it's very easy to show that actually the action of the Casimir acting on C infinity of X and R is just given by minus the Laplacian of X. So in other words, the action of the Laplacian on X comes from the action of a canonical invariant differential operator acting on the group. Now the final thing I'm going to say is that I will introduce the constant Dirac operator. Okay, so you see our purpose is to compute the trace of the heat kernel on functions. But still, to compute it, we're going to introduce again Dirac operators, but in a different way. It's a different kind of Dirac operators than the one I talked about. So the Dirac operator of constant was introduced by constant. I will introduce this one, d hat k. This is for constant. It is not for the maximal compact group. So this operator is a section of the Clifford algebra of G tensored with the enveloping algebra of G. Okay, so the enveloping algebra of G, we know that these are the left invariant vector fields. These are left invariant differential operators on the group G. And it can be actually understood as the quotient of the tensor algebra by the relations defined by Lie brackets. Okay, so this is an easy thing. And we see now this Clifford algebra. Okay, so the Clifford algebra here is associated to the bilinear form minus B. So remember that the Lie algebra is equipped with a bilinear form. It's not a scalar product, but you can still define the Clifford algebra with the commutation relations E prime plus E prime E is equal to 2B E of E prime. This is this Clifford algebra, C hat of G. So I will just explain how is this Dirac operator constructed. So it's a completely different sort of Dirac operator. So it's given by the formula d hat of G hat k. So I rewrite it as C of EI star times EI. So this lies in the Clifford algebra C hat of G, and this lies in U of G. And then I have plus 1/2 of C hat. Okay, maybe I will write this as chi j. Okay, so I will explain what this is. So let me explain what this is. So this looks like a Dirac operator. It's Clifford multiplication times differentiation. And then there is this extra term. So on the Lie algebra of the group G, you have a canonical 3 form, which I write chi G, which I define this way, U VW. So it is given by B of U VW. So it's extremely easy to see that okay, maybe I should have said that this bilinear form is tautologically by construction ad invariant, ad of G invariant. That is, it is invariant by the adjoint of G, of the group G on the Lie algebra. Okay, so typically that's a killing form, which has this property. So this chi G U VW, this is very simply because of this property of isometric action of the group G. This actually is antisymmetric to 3, 4. So this lies in lambda 3 of G star. This chi G defines an element of lambda 3. And this is a corresponding element in the Clifford algebra. So in other words, I explained at some point that as vector spaces, the Clifford algebra and the exterior algebra are the same. So this term also lies in the Clifford algebra of G. And so the remarkable thing proved by constant is that actually this operator is a sort of square root of the Casimir operator. So let me just quote. This is live. So theorem constant that the square of the Dirac operator is given by minus Cj plus a constant, an explicit constant. Okay, so what is remarkable about this result is that Cg in some sense is a scalar operator. I mean, it's scalar in the sense that it only involves vector fields. There is no matrix thing. And you find that it is the square root of some matrix operator. So, of course, up to some constant. But, you know, Dirac, again, when Dirac worked, he tried to find the square root of the Laplacian acting on a vector space. And he got the flat Dirac operator. So actually, it's remarkable that with a non-flat structure like a Lie group, the Casimir operator almost has a square root, which is a differential operator. Okay, so what are we going to do with this? Now, we just go back to the question of computing. You know, I just go back to the question of computing the trace of exponential delta x over 2. My original question of computing the trace of the heat kernel. But now I told you that this is just a trace of the action of minus t times the Casimir of g divided by 2. So in other words, we know that the Laplacian on the symmetric space X, well, I mean, I'm cheating a bit here because X is non-compact, so one has to take this with a grain of salt, okay? So actually, to make what I say rigorous, maybe I should go to a compact quotient of the symmetric space by a discrete group. But I'm not going to do this because that would be notationally embarrassing. So let's forget about this question of non-compactness. So I write it this way. And now I'm going to use the fact that this minus Cg is just a square root, so this becomes the trace of exponential t d hat k squared over 2 plus t times a constant. Right, I just replace this minus Cg d hat, okay, maybe it's minus, it doesn't matter the sign of the constant. And so what we discover, and I discovered this with amazement, is that we find again trace of exponential of something to the square, which is exactly what I had before in index theory. Okay, I'm now suddenly, without having done anything, in exactly the same formalism. So of course, what's wrong with this is that the operator d hat k does not act on smooth functions. Okay, the Casimir acted on smooth functions. The operator d hat k does not act on smooth functions. So, in other words, the fact that this is the square of d hat k cannot be exploited exactly as I did in the case of index theory, because simply, in some sense, I took the square root of the operator, but this square root lies in an extension of the space of operators, and so it doesn't act anymore on the original space on which I wanted to act. So I'm stuck. But actually I'm not stuck. I'm not stuck because what I'm going to say is that actually C hat J acts on the exterior algebra lambda of G star. So this is a general fact again. I explained that the exterior algebra is always a Clifford module. So what I'm going to say is that this operator d hat k acts on C infinity of G with coefficients in the exterior algebra lambda of G star, sorry. So I go back to X, I go back to G, sorry. So I'm saying simply by its structure, this d hat k acts on sin infinity of G with coefficients in lambda of G star. This is because the Clifford algebra acts on lambda of G star, and the differential operators acts obviously on smooth functions. Okay, you could even formulate this as tensor product of these times these. Now, I'm almost done now, because on P plus K, these are two Euclidean vector spaces, and on these two Euclidean vector spaces, I'm going to do the construction that I outlined before in the case of vector spaces. So I will introduce S of P star tensored with lambda of P star, and S of K star tensored with lambda of K star. And then, okay, so on this space here, I have dp plus the theorem operator plus its adjoint. We saw what it was. It is a contraction. We have here actually dk plus dk star. Okay, but actually, I mean, I'm sorry, I have to do some manipulation here because I have to take into account the fact that B is positive on P and negative on K. So one cannot treat P and K on the same footing. Okay, and when squaring this, it doesn't change anything. But it's important for the sequel. So these operators, they act on what? They act on this, and this operator acts on this. So definition, so let me define the operator dB, which is given by d hat k, plus 1 over b, dp plus dp star, plus I dk minus dk star. And so this acts on C infinity of G with values, let's say, in the symmetric algebra of G star tensored with the exterior algebra of G star. Okay, so in other words, this piece here acts on this symmetric times exterior. And the other piece acts on smooth functions with values in the same thing. So ultimately, we get a full operator. Well, unfortunately, I have to add a third term, but I will not explain this one, but if I did not add it, nothing would work. This would be square root of minus 1 Clifford of yk bracket yp. Do not worry about this. You cannot, I mean, I just added, but I won't explain what it is. It is actually a bracket of yk and yp. So, once we have this, we are going to quotient everything by k. Ultimately, we are going to quotient this. Okay, this operator is invariant under the action of k, and so it descends to an operator acting on the smooth sections of x with values in the symmetric algebra, I would say, of G star. Maybe I will put a bar here, tensored with the exterior algebra of G star. Where G bar is just the quotient. So we're almost done here, because this actually is just what I talked about before as being saying that I want to introduce the relative theorem complex of some vector bundle. I told you if I want to have a resolution, I want to have a resolution by some vector bundle over X. And here is a vector bundle. That's a vector bundle G bar. So in other words, with respect to what I explained before, I will do G bar equals to E. Okay, so ultimately, so the operator descends to these, and definition, I define LB of X to be dBx squared minus d hat k squared. So, let me just give what is the structure of this operator. Okay, so we will use Bargmann isomorphism. Now we're going to use Bargmann isomorphism. Okay, so let's see. This space is a space of sections over the symmetric space X of an infinite dimensional vector bundle. Infinite dimensional vector bundle. This is something which is, in harmonic analysis, is never done for various reasons, but in this context it will be possible to do. So we use the Bargmann isomorphism, which allows us to identify this space more or less with a space of smooth sections over the space X script of the pullback of the exterior algebra lambda of G star. And the space X script is just the total space of the vector bundle G bar. And G bar splits as Tx plus n. Okay, in the same way at the Lie algebra G splits as P plus K, the splitting descends to a splitting of G bar as Tx plus n. So, what this allows us to do is to say, having this infinite dimensional symmetric algebra is equivalent to increasing the space to X script, which is now a fibration over X. And now we're going to write this operator in the proper with the proper setting, analytic setting. So theorem. I just give a few parts of this operator. So first piece is just the harmonic oscillator along the fiber. So this is just the harmonic oscillator along the fiber. So remember, I told you that I have to introduce a vector bundle, so I have it, which is Tx plus n, and then I have the number operator of, I have 2b squared here, over b squared, and then I have a second term, which is essentially the geodesic flow, and then other matrix terms. Okay, so our operator is no longer an elliptic operator. It is an operator which is degree 2 along the fiber, essentially a Laplacian plus y squared minus the dimension, minus m minus n, that's the dimension of p plus k. And there is this here. So if y tx lies in this fiber tx, it defines a corresponding vector field, horizontal vector field, on the total space of the fibration. And this is a so-called geodesic flow. That's a vector field which generates the geodesic flow. So such kind of operators were actually introduced a long time ago by Kolmogorov. Kolmogorov were just introducing operators on R2. They were just much simpler operators. But let me just state what the formula is. A very simple formula in the case where we take as Lie group G. We just take the G equals R as a Lie group with K equals 0. So the Lie algebra G is just R again, and of course P is R and K is 0. So in this case, the operator LB, I just write it. It's very simple. 1 over 2p squared minus d squared over dy squared plus y squared minus 1 plus the number operator on the exterior algebra of y squared divided by b squared. And there is just here minus y d over dx over b. So an operator like this was considered by Kolmogorov. There was nothing, none of this. There was just this piece here and this piece. So operators of this kind, they are not elliptic because they just differentiate once in the base direction while differentiating twice in the fiber direction, so they cannot be elliptic. But they are hypoelliptic. So hypoelliptic means that from the analytic point of view, they are almost as good as the elliptic ones. In particular, they do have heat kernels. So let me now consider a compact quotient of the symmetric space by the action of a discrete group. So let gamma be a co-compact, torsion-free, discrete subgroup of G. So in this case, you can form the quotient Z equals the quotient of gamma x mod gamma. This is because the group G acts on the left on the symmetric space, so we can form the quotient, and so this will be a smooth compact manifold. Okay, so all the constructions I gave being equivariant, they all descend to the compact manifold Z, and so I will state the following theorem. The trace of the heat kernel of Z is equal to the supertrace of exponential minus t LBZ for any B. So again, this is a scalar trace, and here we have a supertrace because we are acting on sections of a Z-graded vector bundle, so we have alternate sum of traces. So this sort of result exactly says, I cannot show in detail, but that's exactly what I wanted to have. I've expressed the trace of G acting on the space of smooth functions as the supertrace of some heat operator acting on a bigger space, which turns out to be a resolution of the original space of smooth functions. Okay, so this is not totally straightforward to prove. This is not too difficult. And then we will try to go make B tend to plus infinity. Now, it turns out by a very simple scaling argument that when B tends to infinity, this piece becomes dominating, or if you like, in this operator, this piece becomes dominating, and so the trace or the supertrace tends to concentrate on closed geodesics. So tends to concentrate on closure disks. So exactly in the same way as in index theorem, we concentrate on points. Now the heat trace concentrates on closure disks. So there is even more than this, because actually you can split each of these traces or super traces according to the pi1. I mean, you do what Zelbergs did. You can express each of these traces as sum of so-called orbital integrals. So that's like by a Poisson summation method. You just re-express the trace as sums of heat traces on the universal cover, and actually each orbital integral is preserved by the hypoelliptic deformation. So that ultimately it is possible to make B tends to infinity in this identity. Okay, so I will not explain the analysis, except that now basically we are moving to doing hyperbolic geometry. We are doing hyperbolic geometry. You have to do hyperbolic geometry and analysis on the symmetric space X, where in particular we're fighting the fact that the geodesic floor is hyperbolic, or is ergodic if you like. I mean, it's hyperbolic, so ergodic, so basically it is very unstable. So the explicit computation as B tends to infinity can be done. And so as an example, I just say that this method gives you the original Zelberg's trace formula. So the original Zelberg's trace formula was valid just for Riemann surfaces, first of all. But what I'm talking about is valid for arbitrary symmetric spaces of compact type with completely explicit formulas. And actually these formulas look like exactly integrals over X, I would say, of A roof of Tx Ch of E. Okay, I cannot explain, unfortunately, I do not have time, but as we could expect, since we formulated the evaluation of the original trace of a heat kernel as an index problem, the final answer is exactly formulated in terms of characteristic classes, A roof, and Chen character. Okay, so it turns out that this is not an evaluation of cohomology classes, so you should put this in brackets, but in some sense it gives to the Zelberg's trace formula exactly the structure of an index problem. If you like, when you think of the formula of Riemann-Roch-Hirzebruch, you have original formula of Riemann-Roch, valid for Riemann surfaces, where you do not see the third class, you just see 1 plus half of the C1 of X, and you do not see the Chen character, you just see the first Chen classes. So you only see things with Todd and Chen in high dimensions. The same thing here. In Zelberg's original formula, you do not see the proper setting with A roof and Chen. You only see it in higher dimensions. So I will not give you the formula how it looks like. It's not a complicated formula, actually. Not too complicated. But so ultimately, what is the content of index theory applied to locally symmetric spaces? It is like a Poisson formula, and the coefficients of this Poisson formula are themselves sort of pairings of A roof class with Chen character forms. Okay, so to conclude, what I have done here is very different than what we did before, in the sense that before index, we had a well-defined operator, and we had the index, and we computed its dimension, or its Chen character, or its refined properties. That's what we did in the first part. In this last part, we have a different problem. We are computing the trace of an operator on the infinite dimensional vector space. And we want to give a local formula for it. So we set up the proper cohomological theory so that the space of smooth functions becomes the cohomology of some explicit complex, And in some sense, you might think, okay, we're complicating the problem. Of course, when we replace the cohomology by a resolution, we complicate the cohomology. But of course, we can use the resolution. We now use this resolution analytically so that ultimately we can localize the trace or the supertrace on closed disks. Okay, I think I will stop here. Thank you very much.